Good morning, everyone, and thank you for being here. Today, we'll be presenting a project titled AI for Institutional Kitchen Schedule. This was done as part of Advanced Artificial course under the guidance of Dr. Arijit Mandal. Let me introduce our team. I am Vishwasputh, and I worked on the architecture and methodology. Along with me, we have Pranshu Prasad, who focused on algorithmic structure and simulated annealing logic, Shavankar Shah, who handled implementation and optimization evaluation, and Ayush Kumar, who took care of constraint modeling and DAG construction part. The project you are about to see aims to solve a very real-world problem: how to efficiently run a large-scale institutional kitchen. It's one of those problems we take for granted, but it's incredibly complex under the hood, like solving a daily puzzle with people, tasks, time, and equipment. Let's start with the core problem. Large-scale institutional kitchens like those in college hostels cater to hundreds of people every single day. These kitchens must prepare multiple meals type at once, such as vegetarian, non-vegetarian, Jain meals, and more. Now imagine that for each meal type you have dozens of subtasks, from washing and chopping to boiling, frying, and garnishing. Each of these tasks depend on others. For example, you can't start frying before chopping, and you can't chop before cleaning. These are called task dependencies. On top of that, the resource like stoves, sinks, and utensils are limited, and you also have a finite number of cooks who can only do one task at a time. So the problem becomes a massive scheduling challenge. We are trying to assign the right task to the right cook at the right time using the right resources, all while ensuring the kitchen runs smoothly and meals are ready on time. Let's break down the constraints we had to handle. First, we use directed acyclic graphs or TAGs to model the task dependencies. That means each task must be scheduled after its prerequisites are completed, just like a cooking recipe in steps. Then there are resource constraints. A stove can't be used by two people at the same time. The same goes for mixers, ovens, or even sinks. Each cook must only be assigned one task at any point in time. Also, the number of tasks must be spread out properly so no one is overloaded or ideal for long stretches of time. Another major challenge was batch processing. Some dishes are prepared in batches, and processing time changes depending on the size of the batch, which adds complexity to the calculations. And finally, we must ensure that all dishes are ready together, because you can't serve half a meal. These constraints mirror real-world kitchen dynamics, making the problem both interesting and complex from an AI perspective. Based on those constraints, we defined multiple optimization objectives. Our primary goal was to minimize the make span, that is, the total time it takes to prepare all meals. A shorter make span means fresher meals and better kitchen efficiency. But we also looked at secondary objectives like ensuring the workload is evenly distributed among all cooks, making sure kitchen resources are used to their fullest potential, no idle equipment, identifying opportunities for parallel processing. For example, while one dish is boiling, another can be chopped by a different cook. And lastly, determining optimal batch sizes for tasks that are repeated or shared across meal types. So, in short, we wanted a solution that was not just but fair, efficient, and realistic in its approaches to real-world kitchen workflows. To tackle this, we explored three different AI-based approaches, each with its own strengths. The first was using a constraint satisfaction model with the Z3 solver. This is a more formal mathematical approach where all constraints are modeled and the system finds the most optimal combination of task assignments and timing. It's highly precise but can become slow with large number of inputs. The second was a heuristic-based method which uses more practical tool-based logic. This method is faster and easier to scale but may sacrifice a bit of precision. The third, and quite interestingly, we applied a meta-heuristic technique known as simulated annealing. Inspired by the process of metal cooling in physics, this method allows the algorithm to explore a wide range of solutions and gradually settle into the best one. It's especially powerful when the solution space is large and complex. All three methods were implemented, tested, and evaluated, and each showed unique benefits depending on the constraints and scenario size. In the next few slides, we'll walk you through the methodology, implementation, and results for each of these approaches. We'll also compare their performance and show why AI-based scheduling can truly make a difference in institutional kitchens.
Hello, I am Ayush Kumar. I'll be solving AI-based scheduling optimization for institutional kitchens using directed acyclic graphs as a constraint satisfaction problem using Z3 solver. We have used directed acyclic graphs for tasks and dependencies. We have used two types of decision variables, integer decision variables and boolean decision variables. Our objectives are to minimize max completion time and to balance cook loads. We have used five types of decision variables. First decision variable is start times, where st belong to positive integer and t belong to the tasks. Our second is a boolean integer variable of 2D array of dimensions c and t, where c are number of cooks and t is the task. xtc is 1 if cook c is assigned to task t, otherwise it is 0. Our third decision variable is activity indicator. It is also two-dimensional array of dimension t and tau, where t is task and tau is the time. Our decision variable a t tau is 1 if task t is active at time tau, 0 otherwise. Our fourth decision variable is max completion time m, where m is a max of task total scheduled. Our fifth decision variable is maximum cook load assigned to each cook. Now we come to the constraints of our problems. Our first constraint is task sequencing. We use this constraint so that, let's say, if we boil in directed acyclic graph, there's a edge from cutting the potato to the boiling of potato, so that then we make sure that the cutting of potato and boiling of potato does not get assigned at the same time. Our second constraint is time bounds, such that each task gets completed within its assigned time and does not take more time than it is assigned. Our third constraint is resource capacity. We have a limited resources available to us, and we make sure that we use all the resources, and if no resources are available, then tasks which require that resources don't get assigned until unless there is a resource, any other resources get free. Our fourth is cook assignment. We make sure that each task needs gets at least one cook. No task will be completed if cook assigned to it is 0. Then we also make sure that a cook can do only one task at a time. This is our fifth constraint. It is for make sure that a cook will be used multiple times, but a cook cannot perform two tasks at the same time. The multiple tasks that will be performed will happen in different time slots. Now we come to the objective function of our problem. We have two objective function. First is a primary objective and second is a secondary objective. Our primary objective is to minimize m. M is the maximum completion time of all tasks available. It is our primary objective. Our secondary objective is to minimize maximum cook load of each cook.
Hello, my name is Priyanshu Prasad. Today I am excited to walk you through the fascinating applications of meta-heuristic, specifically how we can simulate and need to optimize kitchen scheduling. Now, you might not expect kitchens to need advanced algorithms, but when it comes to preparing hundreds of foods with limited staff and resources, the complexity ramps up fast. So let's dive in. Here, the challenge here. Imagine a large kitchen during the lunch service. You have got the vegetarian, non-vegetarian, and Jain meals, each with different food items. These items need to be put, chopped, washed, boiled, often in a specific order. Now throw in limited stoves, pans, and small teams of cooks. Our challenge is to create a schedule that prepares on meals as fast as possible without breaking any dependency rules or overloaded equipment. Sounds simple, right? No. Data modeling. Here, to tackle this, the first step is modeling the kitchen as a data. Each meal type is defined by its food items. Every food item is broken down into subtasks like cutting vegetables or boiling the rice. Subtasks include details like how long they can, what, what tools they need, and how many meals they can be made for at once, and what needs to be done before them. Here, the task processing and dependency graph. Next, we process the task. We calculate how many batches we need. For example, if cooking rice serves 10 meals per batch and we need 50 meals, that's a 5 batches. Each subtask becomes an individual task in our schedule with proper timing and dependencies. Then we build a dependency graph ensuring that the clean rice always happens before the cooking of rice. This graph is key for proper sequencing. Here, now we generate a starting point using a greedy algorithm. We topologically sort all the tasks to maintain dependencies. Then, then we assign available resources, making sure we don't overuse any resources, like too many tasks needing a stop at once. This leaves a valid but not necessarily optimal schedule to improve upon. Later, we applied simulated annealing, the meta-heuristic core. Here comes the magic, meta-simulated annealing. Inspired by how metals are cooled, is no need to remove defects. This algorithm makes random changes to the schedule, like reordering tasks, changing the assigned put, or shifting the timing. If a change makes things better, say shortens the total put in time, it's accepted. If not, it might still be accepted, especially early on, to help the system stay not optimal. Over time, the algorithm cools down, becoming pickier about changes. The result, a more refined, high-quality schedule. Here, throughout the process, we track the best schedule found. At the end, the reports how long it takes to complete all meals, whether any constants were broken, and gives the detailed uses, stats, and each cook and resources. This is super helpful for teacher managers. They can balance workloads, spot in the bottlenecks, and better plan their staffing. We should use this approach? So because a real world kitchen are chaotic, task overlap, resources snag, and manual scheduling can't keep up. This approach handles dependencies, adapts to a real-world constant, and produces solid, efficient solutions, even in large-scale kitchens. It's perfect example of how meta-heuristic night simulated annealing can tackle practical, messy problems in everyday life. Thank you. Hope this gave you a tasty and taste of how smart scheduling backed by meta-heuristic can transform the kitchen operations. Thank you.
Hello, today I will be walking you through the heuristic component of a kitchen scheduling algorithm that has been designed to effectively assign tasks, resources, and cooks for preparing multiple types of meals. This algorithm is inspired by the HEFT or the heterogeneous earliest finish time approach, but with several customizations for the unique constraints of a real world kitchen. Now let's break down the heuristic into multiple steps. The first step involves the task graph construction. In this step, it is the main step. In the first step, it is to transform all the meal preparation requirements into a comprehensive task graph where each node in the graph represents a subtask, kitchen subtask, and all these nodes are connected by edges that defines the dependencies between them. So, for example, for a rice to be cleaned, needs to be cleaned before it can be cooked. For every meal and its required quantity, the code calculates how many batches are needed based on the batch size and the operations capacity. This ensures that the scheduling reflects the actual workload for each food item. The second step involves the critical path analysis for task prioritization. Once the task graph is built, the heuristic calculates the priority for each task using a method called critical path analysis. This involves computing the upward rank for every task, which is the longest path in terms of time from the task to any end task in the group in the graph. Tasks on the critical path, meaning any delay in them would delay the overall meal preparation, are given higher priority. The third step involves the priority-based list scheduling with constraints. This is the heart of the heuristic, where we schedule tasks that is based on the priority, where we respect both its sources and the core constraints. So how it works, let's deep dive into it. The first one is the ready task. In this, the algorithm keeps a list of tasks that are ready to be scheduled, those with no unmet dependencies. The second is there are resource checks. Before scheduling a task, we check if there are necessary kitchen resources available. Then we assign the cook to task. The one task that is more complex will be assigned more cooks. Then we schedule where when the resources and the cooks are available, the task is scheduled. Resources are marked as in use and cooks are assigned. The task starts and end time are recorded. And the fifth one is the advancing time. If no task can be scheduled due to resource or cook limitations, the algorithm advances the clock to the next moment when a cook or resource becomes available, ensuring efficient use of time. Now, the fourth step includes the dynamic updates and completion. As all the tasks gets finished, the completion frees up resources and cooks and may unlock dependent tasks. The process continues dynamically, updating the schedule until all tasks are completed. At the end, the heuristic calculates the two important metrics, which is the maximum completion time for all the tasks, representing when the last dish is ready, and the second one is the maximum load on any single cook, helping to balance workloads and avoid burnout. And the fifth thing is why the heuristic that we have used is effective. So this approach combines the critical path, where we focus on tasks that can delay the whole process, resource and co-constraints, and the third one is the dynamic priority driven scheduling, which adapts to changing availability as tasks progress. So the result is a schedule that is both efficient and practical, minimizing the idle time and ensuring that meal preparation flows smoothly from start to finish. So in summary, the heuristic part of this code is quite complex and interdependent set of kitchen tasks and produces an optimized real-world schedule by combining critical path analysis, resource management, and intelligent cook assignment. This not only speeds up the meal preparation but also ensures a balanced and realistic workload for everyone involved. Now, I will be comparing the three methods that have been used in this code. The first one is the constraint satisfaction problem. The second one is the heuristic methods, and the third one is the meta-heuristic algorithms. I will be comparing all these three algorithms and let's find out which one is more effective in which situation. So in CSP, the approach is to find solutions which satisfies all the constraints, and the use cases is in scheduling, puzzles, and configuration problem. It guarantees feasible solution, but that solution is not guaranteed to be optimized, and it struggle with high dimensional problems, which are NP-hard problems. And a second thing that we have used is heuristic methods. Now, it is a kind of rule of thumb strategies. The main use cases is in short-term scheduling, routing. It is fast, but it may settle in local optima. It can never reach the global optima if it has been stuck in the local optima. And it can handle medium complexity, which is better than CSP. And the third one is that we have used is meta-heuristic algorithms. It is kind of a high-level frameworks algorithm and is mainly used for global optimization purpose. And it balances exploration exploitation strategy for near optimal solution, and it is effective for complex